Today we'll explore the consequences of the fact that particles can be indistinguishable, impossible to tell apart. Indistinguishable particles must have no observable consequence of interchanging them, so the probability density associated to their total wave function must be unchanged by interchanging them. There are two ways to achieve this. The first is that their total wave function is symmetric under their interchange. For instance, for the case of two particles, psi x1, x2 equals psi x2, x1. Particles with this property are called bosons. The second way to do this is that the total wave function is antisymmetric under interchange of the particles, which for two particles means psi x1, x2 equals minus psi x2, x1. And particles with this property are called fermions. The fact that particles can truly be identical has far-reaching consequences. Consider the following problem. Consider two independent particles in a one-dimensional infinite potential well of length L. Construct the wave functions and give the energies of the ground state and first excited state of this system if 1. The particles are spin 0 bosons, and 2. The particles are spin 1/2 fermions. What is the total spin of the system in each of these cases? Here I've written the single particle wave functions and energy levels for a particle in an infinite potential well. We'll construct our multi-particle wave functions out of these single particle wave functions. Okay, so for the first case of two spin 0 bosons, each particle will have a quantum number n, referring to this n equals 1, 2, 3, etc. But because they're spin 0, the spin of each particle is just 0, and the magnetic spin quantum number m for each particle is just 0, so these don't differentiate the particles in any way. So all I need to write for my wave functions is this n quantum number, because this can be different between the two particles. Okay, so for the ground state, this will be the state with n equals, say, m equals 1. And it'll be a symmetric combination of psi 1 and psi 1, which is just the product of the single particle ground state wave functions. Psi 1 of x1 times psi 1 of x2. Now, indeed, this is symmetric under interchange of x1 and x2, as it should be for two spin 0 bosons. And the normalization is right because each of these psi 1s are properly normalized. So this whole thing is properly normalized. The energy of this state is just the energy of the individual states added, just E1 plus E1, which gives us pi squared h bar squared over ml squared. So that's the ground state. The first excited state will have one of the particles in the n equals 2 state. So we'll say psi 1, 2, one particle will be in the n equals 2 state. Will now be the symmetric combination of one particle in psi 1 and one particle in psi 2. Now, importantly, because the particles are identical, there is no degeneracy of these states. There's no difference between one particle being the n equals 1 particle and one particle being the n equals 2 particle, or the opposite scenario. So if the particles weren't identical, then there would be a degeneracy of 2 here, but because they're identical, there is no degeneracy. So plus psi 1 x2, psi 2 x1. Okay. And again, this is symmetric under interchange of x1 and x2, as had to be the case for combining two bosons. The energy of this state, I'll call it E12, is just E1 plus E2, the energies of the single particle states added, which turns out to 5 pi squared h bar squared over 2 ml squared. Now, moving on to the case of two spin 1/2 fermions, there, each particle has a quantum number n again, but now because the spin of the two particles is 1/2, they have the possibility for different spin magnetic quantum numbers. So this m could be plus or minus 1/2, which we'll denote in the following as just a plus or a minus for each particle. Now, by Pauli exclusion, two fermions can't occupy the same quantum state. They can't have the same quantum numbers. So in the ground state, where n equals, say, m equals 1, we'd have psi 1, 1 antisymmetric. One electron will have to have m equals plus 1/2, and the other will have to have spin down, m equals minus 1/2, so that they don't have the same quantum numbers. And then they can each have n equals m equals 1. So the appropriate wave function for the ground state is the spatial part of the wave function, which I'll write psi 1 x1, psi 1 x2, times the spin part of the wave function, which will be the antisymmetric combination of one of them having up spin, one of them having down spin. So I'll write that as this, where in this notation, I mean the plus corresponds here to the x1 particle, the minus to the x2 particle, and vice versa here. The first entry in this ket corresponds to the first particle. Then the energy of this ground state is just the same thing as the energy up here, just E1 plus E1, the sum of the energies of the single particle states. Now, for the first excited state, things get a little more interesting. So the first excited state will have one of the particles with quantum number n equals 2, so that the energy level is raised, right? But now, since the two particles have different quantum numbers n, they can have whatever spin they want. One of them could have plus, one of them could have minus, or they could both have plus, they could both have minus, because n and m are different for the particles. So there will actually be 4 degenerate combinations of the spin and spatial wave functions. There will be 4 degenerate possibilities for the wave function of these two particles. So I'll write those 4 possibilities in a second. The spatial part of the wave function, so I'm going to denote that spatial part phi plus minus x1, x2. And that is given by the, it'll be either an antisymmetric or symmetric combination of one particle in n equals 1, one particle in n equals 2. We'll see in a second why it can be symmetric or antisymmetric, and that's because the spin part can also be symmetric or antisymmetric. So psi 1 x2, psi 2 x1. So all the spatial parts of the wave function will take this form. And the possibilities will be so first I'm going to write the spatial parts of the wave function. Okay, so the spin parts of the wave function can have the following forms. There's a possibility that both spin 1/2 fermions have spin up. So this is the spin part of the wave function, and then correspondingly the spatial part of the wave function must be antisymmetric, since this spin part is symmetric and the whole thing has to be antisymmetric. Both could have spin down. And if both have spin down, again, the spin part of the wave function is symmetric under interchange of x1 and x2, so the spatial part has to be antisymmetric so that the whole wave function is antisymmetric. Then we have 2 possibilities where one particle could have spin up and the other could have spin down. And I'll write these possibilities in the following linear combinations. So there's the symmetric linear combination, so plus, minus, plus. So the symmetric combination of one having spin up, one having spin down, and that'll go with the antisymmetric wave spatial part of the wave function, so that the whole thing is antisymmetric. And then there's the antisymmetric combination of one having spin up and one having spin down. And that goes with the symmetric spatial wave function, so that the whole thing is antisymmetric. And there are these 4 degenerate combinations. Okay, good. Where, again, the energies are just the sum of the energies of the single particle wave functions. All of these have one of the particles being in n equals 1, one in n equals 2. So this is exactly the same as the energy we computed over here. Now, in the next part of the question, we want to ask what the total spin of these states is. The important point here is that spin adds just like orbital angular momentum. So if I have 2 particles, one of spin 1, one of spin 2, their total spin has possibilities s1 minus s2 up to s1 plus s2. So for the case of our 2 spin 0 particles, the only possibility is s total equals 0. So our ground state here for the 2 spin 0 bosons would have total spin 0. That's the only possibility. And same thing for our first excited state for the 2 spin 0 bosons. But for 2 spin 1/2 fermions, this total spin could be 1/2 minus 1/2 up to 1/2 plus 1/2. So the total spin could be 0 or 1. For the case of total spin 0, the total spin magnetic quantum number, which is equal to just the sum of the 2 individual quantum numbers, has the possibility of only being 0. And for the spin equals 1, the total spin equals 1 case, this total magnetic spin quantum number equals m1 plus m2 has the possibility of being -1, 0, or 1. So finally, we can look at our fermionic states. In this case, the ground state of this system, we have 1 particle with spin up and 1 particle with spin down. So m1 plus m2 is 1/2 minus 1/2 equals 0. And this antisymmetric combination will really correspond to a total spin of 0. Over here, we had a few possibilities. These 3 possibilities correspond to a total spin of 1. And it's straightforward to see. Here, the total magnetic spin quantum number is plus 1/2 equals 1. Here it's plus 1/2 minus 1/2 equals 0. Here minus 1/2 minus 1/2 equals -1. And these 3 with the symmetric spin states all correspond to the total spin 1 case. And then this state with the antisymmetric combination of spins so that m total equals 0, again, like the ground state, corresponds to a total spin of 0 case. Okay, so what we've learned is that we can combine 2 spin 1/2 fermions to form a bosonic state of integer spin, of spin 0 or spin 1. And in general, this is an interesting feature, that we can combine quantum states with various quantum numbers to get new states with different symmetry properties.